Maybe.
Everyone's attention up here, please. Hey, just a quick review of yesterday. Talked about the natural base E. Okay, remember E is called the natural base. Its value is approximately 2.71828182884. Okay, you keep going. Right? We call it E. It is located on your calculator if you find the button that says E, which I believe is second on the TIA 83s or 84s, is second division. Okay. And then the e to the x power is? Thank you. Second ln. And by the way, ln is the natural log, okay, which we'll talk to a little later. Okay, just to keep in mind as x approaches, if you have this format right here, as x approaches positive infinity, e will approach, this value will approach 2 points, will approach e. Okay? It is when you use E is usually a lot outside when you're dealing with sciences. Okay, we will use it in continuously compounding interest, which we'll talk about here in a minute. But to be clear, E can be in a growth function and E can be in a decay function. Okay, when E is to a positive power, it's a growth function. When it's to a negative power, it's decay. And remember, a negative, tell your neighbor why that becomes decay.
Because it becomes a fraction. Because you can't have a negative exponent, so you flip it. So if it's a negative x, it has to become 1.
Okay. So hopefully we'll take a look at this and remember, if it's a negative exponent, you move it to the other side of the fraction bar, it becomes a positive exponent. So y equals e to the negative x is 1 over e to the x. Okay? So you can have growth and decay. And when you're having, like when, I like to use a leaf, if a leaf falls on the ground and starts decaying, you're using E as part of that decay process. It's a continuous action. It doesn't just pause randomly and stop decaying. Okay, it's continuously doing it. And then we have the continuously compounding interest. And this is one of the pieces that you had on last night's assignment that some of you may not have had realized that you were dealing with. Many of you have maybe accidentally used this format instead. Okay, remember, this is the compound interest formula. Note the difference between the compound interest formula and the continuously compounding interest formula. Okay, we define our rate as E in continuously compounding interest. Our base is E, and then our rate is up here in the power position. Okay, so we call it, a lot of times we just say A equals PERT there, P-E-R-T. Okay, just make sure you understand that you're looking, when you're using this formula, you're looking for the continuously piece. Okay, so if we go to our assignment from yesterday, take a look at, I believe it, what problem was it? Problem 12 and 13. So let's look at those. Okay, some story problems that you had. The populations of Evans City currently is 48,000. Is declining at 2.5% each year. You can model the populations with that formula. And notice that's, with the subscript, they have P of T equals P of C times ERT. Those subscripts just help us determine what population we're talking about. Okay? Where P of C is the current population, and P of T is like our future population after a certain number of years. Okay? R is the rate, the decimal rate of decline per year. Predict the population. So if we're trying to predict this population, P of T, go ahead and tell your neighbor what you put there for your function.
I got for the first one, 25. Actually, that was right there. I should have done it. Yeah. Otherwise, it's broke.
Okay, let's go ahead and take a look at it. So P of T is equal to the current population, which is, Good. 48,500 times E, which we'll just leave as E. And what's our rate? So decimal form 0. Okay. And we're going 0.025. What do I need there? A negative, right? It's declining. Okay, so our rate is declining. And over a certain number of years, well, in this case, they're saying 25. Okay, we multiply it out, we find out the new population after 25 years of decline is 25,960. Now, what happens if you get a number greater than 48,500? You're obviously wrong. How do we know we're wrong? Yeah, it's not going down. It's declining. Okay, it should be decreasing. Should end up with a smaller amount. Any questions there? Glad I could help. All right. Number 13, I want you to tell your neighbor what you did on that one. 13. Take a look at it.
And I got $9,382.78. Yeah. That's
put this over.
Yeah.
Okay, let's go ahead and pause there. So we know we're using the continuously compounding interest formula because it says it continuously or it compounds continuously. That's our key right there. That's how we know we use the PERT versus just regular compounding interest, is the word continuously in there. So it's really important when you see that, maybe circle it, underline it, whatever you have to do. So the amount we need is actually 25,000. So they give us the amount. Okay? Our principal, well, that's what they're asking. How much should your parents invest? That's the principal. That's what we're trying to find. We know E. R is 9.8%, so we need to write that as 0.098. Make sure we change it to decimal. And we're going for 10 years. So when we solve that, really we're trying to get P by itself. How do we do that? We divide by this thing right here. Okay? So if we take and divide by that, that's going to cancel. We're going to be left with P. It's going to bring it down here. And I would probably leave it in this format until I actually do the division. Oops, I missed a 0 there. All right. What's our principal end up being? $0.78. Okay. So we round it up. Very good. Not bad, right? Okay. Matt. Yeah, if you get a bank that's going to continuously compound your interest, you should take the deal. Yes.
So cheap.
Hey, you got not to go a long time into college, but if you keep good grades, when you start going and looking at colleges, they give merit scholarships. They just look at your GPA, some of the schools, and go, nice GPA, you get this much money. Okay, so I don't remember that when I was in college. Not that my GPA was so amazing that they would have given it to me. However, at least my last year was pretty good. Okay, so, I did better. Okay. You guys, most of you have higher GPAs. I was on the honor roll, I'll tell you that. Hey, but in college, dude, I was a beast. Just want you to know. All right. high school, I could have done better. I slacked off too much. But I try to tell you guys how not to do that. Okay? Be good. All right, let's check our work. Number 1, e to the third. Number 2, 5 over 7 e to the fifth. Number 3, 64 e to the negative 14x plus 1 power. And number 4, 2e to the 6x power. Okay, tell your neighbor how you did on those. What kind of questions you have. Can I explain number 3? I can explain it. Yes. I'm going to walk you through what I've done here, and then you guys can ask questions. But I'm distributing the power. So 2 to the 5th is 32. Okay. And e to the negative 3x right there. So I'm just multiplying the 5 by the negative 3 to get negative 15. Okay, so 2 to the 5th, negative 15 to the x, and here I have 2e to the x plus 1. So I'm just bringing this right down. Everyone with me so far? Now, when I'm looking at this, I can say, well, 2 to the 5th and 2 to the 1st is actually 2 to the 6th. So that's 2 to the 6th. So that 32 I had is actually going to end up being 64, right? So 2 to the 5th, which was 32, when we multiply by another 2, we get 64. E, that's a base, and that's a base as well. I have a same base, I just add my powers. So I get negative 15x plus x plus 1, which gives me negative 14x plus 1. And that's as far as I can go on it. Now there are other ways to get to that same place, but that's the work that I did on it. Okay, so first bringing our power to a power, and then combining our like bases by adding the powers. Any other questions? I could. In fact, I already did. There it is. So what I like to do anytime I see radicals is I like to write them as exponents. Most of the time, it's a lot easier. So when I see this whole thing raised to the 4th power, I'm going to write it as this part to the 1/4 and this part to the 1/4. Well, 24x to the 1/4 is 24x divided by 4. Right? Is everyone with me on that? So maybe to break it down even earlier there, I'm taking the 4th root out and I'm raising it to the 4th power, or the 1/4 power. And then I'm distributing the 1/4 to that and to that, which gives me this. And then 24x divided by 4 is 6x. And the 16 to the 1/4 power, or the 4th root of 16 is 2. Bring the x. So this actually should have an x right here. You're just reducing your fraction there. So are you asking how this x became that x?
How it escapes from like the 4th rooting. You don't have to have the 4th root of x. You just leave it as x.
Because when you're counting x's, you guys, this is the same question I've had from about 5 students now. When I bring this 1/4 in, I only bring it to the 24. Remember, the 24, all the 24 is doing right here is it's counting your x's up. So if you have 24 total x's and you divide those 24 into 4 parts, you're left with 6 total x's. Okay, so you're just dividing it there. All right. Hey, numbers 5 and 6. Growth and decay. Did we do 5 as a class? We did, yeah. I was going up by 1s on those. Numbers 7 and 8. Also growth and then decay. All right. Any questions on those? 9 and 10. We started these as a class, at least talking about the shifts. Number 9, the domain is all real numbers. The range, y is greater than -4. If you are struggling with domain and range now, you need to talk to me individually. Okay, you have to get that down. So we need to talk individually if we're still struggling with it. Number 10, all real numbers, range, y is greater than 0. It can't be equal to because 0 is the asymptote. It's never going to actually hit that line even though it looks like it does. Rory? We put it at 2 yesterday. I don't have the page from yesterday. So, hold on 1 second. So, Rory, we started with the y-intercept yesterday at 2, right? And then the 3 moves it over 3 units. That's what that plus 3 does. So we'll shift that over 3. Yeah, I did put a dot there. Yesterday I was just talking about the shifts, yeah. Okay. Nope, that would be a goofy looking graph for sure. Okay. Yeah, no, I was just trying to show the shifts yesterday. So we started at y-intercept of 2, shifts over 3, so that's our new, where our old y-intercept was, is right here. Okay. Yeah?
Are we ever going to encounter exponential growth or decay with the domain? Isn't all real numbers?
No, not this year, you're not. When you're doing growth and decay, your graph is going to continually go out that in all directions for domain. Yeah. Okay, there will be a point, I guess later this year when we do rational functions where we'll have vertical asymptotes. That's next chapter. So, and they kind of look like this. It looks like a branch of the growth and decay. But we're going to get to that later. So, number 11, domain all real numbers, range y is greater than 5. Or less than 5. And we did number 12 and 13. All right. My time is up. Let me know if you have questions.